Good morning. Today we're going to talk about section 7.2, which is entitled Rational Exponents. Well, your knowledge of the word rational should be fresh because we talked about rational expressions in our last chapter. Rational exponents, well, just to review, remember rational numbers, which should have been your first contact with the word rational, are ratios of integers, basically ratios of whole numbers and their negatives. And of course the word ratio is embedded in rational. Ratios of integers is a fancy word for fractions. Rational numbers are nothing more than positive and negative fractions. Alright, so rational exponents should come as no surprise. To define exponents that are fractions, or fractional exponents. Alright, so we're going to be looking at things of the type minus 6 to the minus 2/3 power. We're going to be defining expressions like this, but we need to get some background first before we start juggling around rational exponents. First, I want to talk about fractional exponents, rational exponents, where the numerator is 1. Alright, and then we're going to extend that definition to handle numerators that may not be 1. Alright, so we're looking to define what does it mean to raise a to the 1 over nth power. Motivation. Well, let's start out with a simple example. Let's say I've got the number 7 to the 1/2 power. Let's say I don't know what that means and I want to define what that means. Alright, I'll assign that value the symbol question mark, and I claim that I can raise both sides to the same power and still maintain equality. Alright, so if a equals b, then a squared equals b squared. And we can see that 7 to the 1/2 power squared, well, the rule says when you've got a power of a power, you multiply the exponents, do we not? In other words, x to the mth power in turn raised to the nth power is x to the mnth power. And if I multiply these two exponents as indicated, 2 times a half is 1. So that tells me question mark squared equals 7 to the first power. Well, of course, 7 to the first power is just 7. So if question mark is the quantity I squared to get 7, that means question mark is the square root of 7. Okay? So that tells me that 7 to the 1 over 2 power is really equivalent to the square root of 7. Alright, so that's a bit of an informal proof of what it means to raise a to the 1 over nth power. Nothing secret about 7 or 2 here. I could have taken any base and played this game. Let me get a fresh screen. I claim by that above rationale that, well, I could claim 7 to the 1/3 power is the third root of 7. Could I not? 7 to the 1/4 power I claim is the fourth root of 7, etc. In fact, I could claim any base to the 1 over nth power is equivalent to the nth root of that base. And that's how we define a fractional exponent, a rational exponent, when the numerator is 1. And of course, the denominator can be any integer not equal to 0. Alright, let me exploit this definition and simplify something of the type 8 to the 1/3 power. Well, by this definition, 8 to the 1/3 power is really the denominator root of that base, namely the third root of 8. And of course, we know from last section that the cube root of 8 is 2. Similarly, 9 to the 1/2 power. Well, if I take the second root of 9, I can rewrite this expression, if my numerator is 1, as the second root or the square root of 9. Remember, when no index is specified, we assume a second root, and the square root of 9 is, of course, positive 3. How about another example with a fractional exponent where the numerator is 1? Minus 64 to the 1/3 power. Well, the rule says all you need to do is take the denominator index root of that base to express it equivalently. And I know that the third root of minus 64 is, of course, negative 4, as in our last section. How about 16 to the 1/4 power? Well, if the numerator is 1, just take the denominator root, the fourth root of 16. And, of course, the fourth root of 16 is positive 2. How about something a little nastier? How about minus 1/32 is going to be my base, and 1/5 is going to be my fractional exponent. Alright, now don't panic. This negative sign hanging out in front here, all that is a factor of minus 1, but notice that factor of minus 1 happens outside of this exponent process. Exponent first, multiplication later. Alright, what's 1/32 to the 1/5 power? Well, if my numerator is 1, I just take my denominator root. Hang on. I'll carry that minus 1 factor to my final answer. It's minus 1 times the fifth root of 1/32, right? And the fifth root of 1/32 is, of course, a half. A half times a half times a half times a half times a half is 1/32. And, of course, minus 1 times 1/2 is negative 1/2. So my final return for this example is negative 1/2. Okay? Alright, let's talk about some more complicated examples. Simplify. We know we can simplify root expressions, hence we can simplify rational exponent expressions because those are really roots. If I've got minus 27x cubed raised to the 1/3 power, again, if your numerator is 1, a fractional exponent, all that means is you take your denominator index root. So I claim that's going to be minus 27, the third root of minus 27 x cubed, and of course that turns into a minus 3x. Simple root example, right? Simplify. Again, another expression. 256 times a to the 8th power to the 1/8th power. Alright? Again, if your numerator is 1 on that fractional exponent, you just take your denominator root, the 8th root of 256 a to the 8th power. Well, the 8th root of 256, I believe it's 2. I'll leave that for you to confirm. 2 to the 8th power is 256. I'm not going to write out 8 factors of 2 and do it from first principles. So I claim the 8th root of 256 is 2, and the 8th root of a to the 8th power, well, of course that's just a, but again, notice my index is even here, and I cannot allow for the possibility of negative roots with even indexes, so I've got to wrap that a in absolute value symbols to be totally formally correct about it. So there's my final return, 2 times the absolute value of a. Another one, simplify. Yeah, let me get some more room here. Simplify 25 times b to the 4th power in turn raised to the 1/2 power. Well, we all know that raising something to the 1/2 power is totally equivalent to taking the second root, or the square root, of that expression. And of course, the square root of 25 is 5, and the square root of b to the 4th power is, of course, b squared. And because b squared is always positive, we do not have to wrap anything in absolute value symbols here. Simplify. Minus 2, 5, 6 x to the 4th power, in turn raised to the 1/4 power. Well, as we know, if we have a fractional exponent and if the numerator is 1, all I need to do is take my denominator root, the 4th root of minus 256 x to the 4th power, and of course you'll spot our index is even and our radicand is negative, and that cannot happen. We claim not real is my appropriate response here. Alright, so we have hammered home the fact that x to the 1/nth power is in fact the nth root of x. We proved that somewhat informally. Well, let's extend that idea. How about if you've got a fractional exponent where your numerator is not 1? Right? Well, again, I'll give you a proof by example, so to speak. Let's say I've got 8 to the 2/3 power. Right? I claim I can break up that exponent as 1/3 times 2, and I know when I take a power of a power, I multiply the exponents, right? So I can rewrite this expression as this expression. It's 8 to the 1/3 power times 2. So essentially I take my denominator root first. 8 to the 1/3 power, well, I know that's the third root of 8, and that's 2. And 2 squared is, of course, is 4. So I basically just justified how to handle expressions of this type. Basically, I can take my denominator root and then raise to my numerator power. All right, notice, I could have also done it like this. 8 to the 2/3 power. I could claim that is equivalent to 8 squared times 1/3, or 8 squared raised to the 1/3 power. Let me make that a little clearer. Again, when I take a power of a power, I multiply the exponents, and 2 times 1/3 equals 2. So 8 squared to the 1/3 power, well, let's see, I take 8 squared, that's 64. So that's equivalent to 64 to the 1/3 power, and I know that's also 4. Notice these two answers agree. So if I'm evaluating a base to a fractional exponent, I can take the denominator root first and then raise to the numerator power. Or I could raise to the numerator power first and then take the denominator root. Often we do it we take the denominator root first because we could end up with cumbersome values if we don't. Let me show you some more examples. But before I do another example, let me write down the formal rule. It says x to the m over nth power. Well, I could take the nth root of the denominator first and raise to the mth power. Or as we saw in that previous example, I could raise to the numerator power first and then take the nth root. Alright, both of these are equivalent and correct ways to attack problems of this type. The idea is we usually do it this way: take the denominator root first if you raise to the numerator power first, you could end up with cumbersome values that you may not be able to easily identify the root of. All right, but technically you should be able to handle it each way. Let's do some examples. Evaluate. Evaluate means answer with a value. Should get a number for an answer here. 32 to the 2/5 power. Well, if I take my denominator root first, I'll get the 5th root of 32 and then raise to the numerator power squared, right? Alright, this turns into an easy problem. If I take the denominator root first, the 5th root of 32 is 2, and of course 2 squared equals 4. Not so tough. Try another one. 81 to the 3/4 power. Again, usually we take the denominator root first, the 4th root of 81, then raise to the third power. Of course, the 4th root of 81 is 3, and 3 cubed is positive 27. Another example. Minus 64 to the 2/3 power. Notice we've got fractional exponents here where the numerator is not equal to 1. I'll take the 3rd root of my base first and raise to the numerator power. The cube root of minus 64 is of course negative 4, and negative 4 squared is of course positive 16. And let's see, this one's kind of nastier. We've got a fractional base raised to a fractional exponent with a negative sign sitting out in front. And remember, that negative sign gets dealt with last after I evaluate this base at this power. Alright, so I'll just carry a factor of negative 1 into my final answer here. What's the square root of 1/25? Well, of course, that's 1/5. And 1/5 cubed is then going to be a 5th times a 5th times a 5th. That's going to be 1 over 125, of course. And minus 1 times 1 over 125 is, of course, negative 1/125th. Alright, so a bunch of examples there of how to handle expressions with fractional exponents with the numerator not equal to 1, or perhaps not equal to 1. Let's see if we can climb up the ladder a little here. Simplify. Here we're dealing with variable expressions raised to fractional exponents. Well, I'm still going to do it the same way. 2nd root first, the square root of 4c to the 4th raised to the numerator power. Denominator root, numerator power. Alright, what's the square root of 4c to the 4th? Well, of course, that's 2c squared. No absolute value symbols needed. And finally, 2c squared cubed is going to be 8c to the 6th. Oh, I almost wrote c to the 4th. 8c to the 6th, right? Simplify. Minus 27 m cubed n cubed raised to the 2/3 power. Alright. Now, after a while, after you practice these a bunch, some of these you can do in your head, I'm going to take the 3rd root of this base. Can we do that in our heads? The 3rd root of minus 27 is negative 3. The 3rd root of m cubed is m. And, of course, the 3rd root of n cubed is n. So I'm going to have minus 3mn raised to the 2nd power, which, of course, reduces to 9m squared n squared. So often on some of these simpler ones you can do it in your head. Denominator root, numerator power. Try this one. Simplify. Negative 32a to the 10th power raised to the 3/5 power. And I'm going to take that negative sign and write it as a factor of -1, and that happens outside of the exponent process. Well, what's the fifth root? Let me write it out. The fifth root of 32a to the 10th power. Denominator root of that base in turn cubed. Well, we know the fifth root of 32 is 2. What's the fifth root of 8 to the 10th power? Now please convince yourself the fifth root of 8 to the 10th is a squared. A squared is the quantity we raise to the 5th power to get a to the 10th. And don't forget, you also have to work that numerator exponent now that you've cleared away the root. Alright, so I've got -1 times 2 cubed is 8. A squared cubed is a to the 6th. So my final answer here is going to be -8 times a to the 6th power. Alright, final answer for this example is right there. Alright, so we've talked about fractional exponents where the numerator was 1. We talked about fractional exponents where the numerator is not 1. One thing we did not talk about is fractional exponents where the exponents are negative. And that always seems to bring problem. Negative exponents always seem to bring unpleasantness. Well, the idea here is you've got to practice these to get them straight. We know from chapter 5 our definition for negative exponents says x to the minus m is 1 over m, and of course 1 over x to the minus m is positive x to the mth power. Alright, that's from chapter 5. Our two rules on how to handle negative exponents, not fractions. Alright, what happens? Well, we can extend that idea. I mean, fractions are numbers too. I claim x to the minus m over n is nothing more than 1 over x to the m over n, and then I can simplify that as needed. Similarly, 1 over x to the minus m over n is going to be x to the positive m over n. Alright, so this idea for negative whole number exponents carries over to negative fractional exponents. Alright, let me get a fresh screen. We'll run through a bunch of examples. Simplify and express with positive exponents only. Alright, we've got 9 to the minus 1/2 power, and by definition it's going to be 1 over 9 to the 1/2 power, is it not? And I know that 9 to the 1/2 power is nothing more than the square root of 9 in my denominator, and the square root of 9 is of course positive 3. So the answer to this evaluation is simply the number 1/3. Alright, so I'm going to say simplify and express with positive exponents only. I'm going to abbreviate that with the acronym simplify and express with positive exponents only, so I don't have to keep writing it down over and over. SAUPIO, simplify and express with positive exponents only. So I'll invoke that here. express with positive exponents only. The idea is when you have positive exponents only in your final answer. 36 raised to the minus 3/2 power. Students tend to give all kinds of crazy answers for problems like this, but it's really not that bad if you stick with the system. Well, anything to the negative power is 1 over anything to a positive power, so that would probably be my first step. Now in the denominator, I'll take my denominator root, well, the square root of 36 is 6, and raise that to the 3rd power, and of course 6 cubed is 1 over 216. 6 cubed is 216 in the denominator. So there's my final result for this simplification example. Let's look at a variable expression, simplify and express with positive exponents only. Let's say I've got minus 27a cubed raised to the minus 2/3 power. Alright. Again, if I've got something raised to a negative exponent, I claim that's equivalent to 1 over that something raised to the positive exponent. Informally, I like to think of it as flipping downstairs and changing the exponent sign. Alright, working the denominator now, what's the 3rd root of minus 27a cubed? Well, of course, that's minus 3a. And now I'll work with the numerator power. Minus 3a squared in the denominator is going to be 9 times a squared. So I've simplified as much as I can and returned an answer with positive exponents only. Again, simplify and express with positive exponents only. Minus 1 over 81 to the minus 3/4 power. Alright, if I've got a negative exponent at the numerator level, I move it downstairs and change the sign of the exponent, and similarly for negative exponent expressions in the denominator. I can move this upstairs. It's 81 to the positive 3/4 power, and of course my denominator reduces to 1 then, and I won't write a redundant denominator 1. So I claim this is equivalent to minus 1 times 81 to the 3/4 power. The 4th root of 81, well, what's the 4th root of 81? I believe it's 3. And 3 cubed is 27. So my final response is going to be negative 27. Here's a type of problem that's going to occur in your homework list. Simplify the following fractional exponent expression. Well, here I'm multiplying two identical bases but to different fractional powers. And you recall in chapter 5 we saw that when you multiply the same base expressions, you equivalently keep the same base and add the exponents. Same deal here, except my exponents are fractional. Right, so I've got 5 to the 2/7 plus 3/7, and of course adding those exponents gives me 5 to the 2/7 power. And I can't really do much else with that. 5 is not a 7th power of any integer. It's not a perfect 7th power, so that's as simple as I can get for that particular problem. Try another one. Simplify. 11 to the 2/7 power, in turn raised to the 3rd power. Well, let's see. Power of a power, you multiply the exponents. Remember in chapter 5, if you've got x to the nth power in turn raised to the nth power, you multiply the exponents. Nothing new there. Same deal here. Power of a power, I multiply the exponents. Well, 2/7 times 3 is, of course, 6/7. I don't need parentheses here. I can just write my answer as 11 raised to the 6/7 power. 3 times 2/7 is 6/7 at the exponent level. Alright, another. Simplify. Let's say I've got a product with two factors, two different bases with two different fractional exponents, and they are in turn raised to an outer exponent. Well, we know again in chapter 5 said that if you've got a product in the base raised to a common power, I can distribute an exponent over a product base. Well, same deal here. Again, I don't need to know if we need to be so formal about it. I'm going to take both factors of that base and raise them to the same exponent and then multiply the result. Well, this is now a multiplication problem at the exponent level, of course. 2/3 times 6 is 4. So I'll have a to the 4th power times, and now a power of a power here. 1/2 times 6 is, of course, 3. I get a to the 4th times b cubed. Our author would probably write this answer as a to the 4th b cubed with implied multiplication. Alright, let me get a fresh screen. I think it's going to be our last screen of the day. I think there's 2 more examples I want to do. Simplify the following rational exponent expression: a to the 8/3 power times a to the 1/3 power, all divided by a squared. Alright, so let's take it a step at a time here. I don't see any negative exponents here, so all I'm going to do is multiply this product, and when you multiplying exponent expressions with the same base, you keep the same base and add the exponents. Again, I don't know if you really need to be so formal here, but I'll write out that step. In the numerator, a to the 8/3 times a to the 1/3 is a to the 8/3 plus 1/3. Of course, at this exponent level, 8/3 plus 1/3 is 9/3. And of course, 9/3 is 3, so I really reduce to a to the 3rd power over a squared. And of course, a cubed over a squared is a. So my final return for this example is the single variable factor a. Alright, one more, and it's a little bit of a nasty one. I think this was one of the last ones on your homework list. Simplify n to the 1/5 power times n to the 2/5 power minus n to the minus 1/5 power. Alright, we've got a common factor sitting outside of a binomial sum or difference here. So I've got to apply my distributive law. I've got to take this expression and distribute. Multiply by each term in that difference. And let me go ahead and formally write it out. I'll have n to the 1/5 times n to the 2/5, and I'll worry about that later, minus n to the 1/5 times n to the minus 1/5, and I think you'll see something happening here. Alright, multiplying these two same base expressions, again I keep the same base and add the exponents, so I'll have n to the 3/5 minus, well, if I multiply this expression, I notice the exponents are fractional and opposites. It really turns into an n to the 0 power, so not as tough as you might think. So I reduce to n to the 3/5 power minus 1. Again, anything to the 0 power is 1. Alright, oh, I got one more. Sorry, did I say two more? Did I say one more? Just one more. Again, this is from your homework list, so I'm doing you a favor. Simplify last one, I promise. Minus 8a cubed b to the 6th to the minus 2/3 power. Again, this is one on test day. I'll get all kinds of screwy answers. Not if you just take your time and apply the rules step by step. Again, the first thing I'm going to recognize is that negative sign has nothing to do with the exponent process. Okay, so right away I'm just going to remember to grind out the exponent expression and then remember to throw in a factor of minus 1 in my final answer. Alright, minus 1 times anything to a negative exponent is 1 over anything to the positive exponent, remember? By one of our two rules for negative exponents. So I claim that exponent expression is really equivalent. Make sure I copy it right. To 1 over 8a cubed b to the 6th raised to the positive 2/3 power. Alright. Now I'll get to work with the fractional exponent. I'll take my denominator root. Well, the cube root of 8 is 2. The cube root of a cubed is a. And the cube root of b to the 6th is b squared. So I'll take my denominator root of that denominator expression and then raise to the numerator power. And it's beginning to look good. I think we can all see minus 1 times 1 is negative 1 upstairs. And downstairs I'll have 4 a squared times b to the 4th power. Here's my final return for the above example. Alright, we're reaching 38 minutes, so we'll call it a day. This concludes section 7.2, Rational Exponents.